This lesson is for sections 2.1 and 2.2 in our textbook titled Graphs of Functions and Relations. Now, our objectives for today are to graph various functions, and this actually should say and relations, without a calculator, so that's really important. We're going to be doing all of this without a calculator, and then we're going to state their domain and range. Now, on the front side of our notes, we're going to be plotting functions. Okay, and on the back side of our notes, we're going to be plotting relations. And we'll talk about the differences between functions and relations tomorrow in our next video. For right now, though, we're going to get an introduction into our next mother function, and this is the square root graph. So we have y is equal to the square root of x. So this is another new mother function. Now, typically, when we graph something and we don't know exactly what it's supposed to look like, we use a table, right, to try to figure out how to plot some points on the graph of that function. Well, in this case, if we use our standard -2 to 2 table, the problem is when we try to plug in -2 into this function here, we end up with the square root of -2. Now this is not possible. We can't take the square root of a negative value, so we can't use -2. That same thing goes for -1 here. We can't take the square root of -1. That doesn't give us a real number. So we have to skip that value and we have to start actually with 0. Okay, so we're going to start with 0. Because we can take the square root of 0. The square root of 0 here is just 0. We can also take the square root of 1. That gives me a nice integer, 1. The problem is when I try to plug in 2, I end up with the square root of 2, which isn't so great to try to plot, right? If I try to come over here and approximate 2 comma the square root of 2, I know it's a little bit more than 1, but I don't know exactly where to put it, so it's kind of going to give me an inaccurate point. So I don't want to use values like that either. If I try the next integer here, if I try 3, again, I end up with the square root of 3, which is not so easy to graph, right? Well, the next integer that I can pick, 4, does give me a nice output. If I plug in, if I use the input 4 here, I end up with a nice y output of 2. So here's my next integer. So see, I have 0, 0, 1, 1, and now 4, 2. Now, if I try to increase my table values here, and let's try to plot 5, hopefully you're recognizing that that won't work either, right? The square root of 5 is not something I can plot very easily. So in this case, when you're trying to graph a square root function, the idea here is you actually don't pick x values. It's faster to choose y values. So my y values here, if I go 0, 1, and then 2, and then 3, 4, 5, and so on, that lets me pick my x values. So instead of filling in a table, okay, normally we just do the left-hand side, right? We fill in the x values first. Instead, you're going to always fill in the y values when you have a square root graph, and you're going to work backwards. So we have our xy table. We're just going to fill in the right-hand column first, and then work our way backwards to figure out what x would equal. Okay, so to do that, what we're going to do is start with our y value, and we plug that in. Okay, so we have y is equal to the square root of x. This is our mother function here that we're looking at. So I'm going to plug in 2 here for y, and then I'm going to try to find x. Now to solve for x here, I would have to square both sides, right? And I end up with 4 is equal to x. So there we go. That's how we got the point 4 comma 2. Now if I do the same thing here by plugging in this here, this y value, I get 3 is equal to the square root of x. Well, if I square both sides here, I end up with 9. So the coordinate here would be 9 comma 3. Now you might be able to do the points for a y output of 4 and 5 easily in your head, right? Because the square root of 16, that would give me 4, and the square root of 25, that would give me 5. And I'm sure most of you would be able to do this table without really having to set up the equations over here. It's when we get into problems like this example here that you're going to want to be able to solve and set up the equations like we did in this example, okay? So let's go ahead and plot this mother function real quick, and we'll move on. So I'm going to plot 0, 0 first, 1, 1, 4, 2, 9, 3, and then 16, 4 is off the graph, so is 25, 5, but we'll just approximate where that one is, 16, 4. Okay, so here is what our mother function for a square root graph looks like. Now, if we talk about the domain and range here, for the domain, remember, we can't plug in any negative values in for x, right? We started with 0. 0 is neither positive, but it's not negative either. We started with 0, so all of our x values are greater than or equal to 0 because we can't plug in a negative value into that function. And you can see here, your graph never crosses the y-axis on this side, right? It never crosses over here. So that's why all the x values, they start here at 0 and they move their way to the right. So they're greater than or equal to 0. And for the range, you can see we have a low point on this graph. The low point here is at y is equal to 0. So everything is greater than or equal to 0 because this continues to positive infinity. If I continue to increase the x values, these y values would also increase to positive infinity. So there's my domain and range, and there's my mother function. Okay, next up is example 2. Now notice inside the radical here we have x minus 4. So we do have a transformation here, and we'll talk about how to graph this using transformations. But first, let's start with our table. So remember, when we see that square root, we're going to pick values for y first. We're going to fill in that right-hand column here. So if I plug in 0 for y, I end up with the equation 0 is equal to the square root of x minus 4. So if I want to solve for x here, I would have to square both sides, and I would get 0 is equal to x minus 4. If I add 4, I get x equals 4. So if I plugged in 4, just real quick to check, you plug in 4 here, and your function, you end up with the square root of 0, which is 0. So that works out quite nice. Then we can go ahead and plot that point for 0. Now do the same thing for y is equal to 1. If we solve the equation, y 1 is equal to the square root of x minus 4, we square both sides. Add 4 and we get 5. So we have the point 5 comma 1. Now most of you will be able to do this in your head. If not though, obviously just jot down this little scratch work on the side, and that gives you nice little values that you can plot on your graph. So let's try plugging in y is equal to 2 here. We have 2 is equal to the square root of x minus 4, square root both sides, add 4, and you get x equals 8. Next up, we have 3 is equal to the square root of x minus 4. Square both sides. Add the 4 and you get 13. And then finally, if we have a y output of 4, that means the square root of x minus 4 has to equal 4. So we'll square both sides. We get 16. So x minus 4 is 16, which means x would equal 20. So let's go ahead quickly and plot these points. We have 5, 1, 8, 2. 13.3 is already off the graph, so I'll just stop right there. And once again, we have, whoops, I kind of missed it, but there's our mother function here that's been translated 4 units to the right. So just to tie it back to the transformations that we learned earlier, notice that we have inside the radical here x minus 4. Now this shifts it right 4 units, similar to when we saw something like the absolute value of x minus 4. That also shifts it right 4 units. Or if we're just looking at a normal function here, we have f of x minus 4. That would shift it right 4 units as well. So it's pretty cool that all of these apply to any type of function. Your transformations will always work. Every single point here has been shifted right 4 units. Now to talk about the domain and the range here, for our x values, notice that your x values this time don't start at 0, right? Because we can't plug in 0 here. If we plugged in 0, we would get the square root of negative 4, which is not possible. So here we started our x values, here's the cutoff on the left hand side, they start at 4. So x is greater than or equal to 4 because they continue up forever to positive infinity. And for the y values, here we're cutting off at our low point here, which is y is equal to 0. And again, they go to positive infinity. So we have y is greater than or equal to 0. All right, next up in example 3, we're going to plot y is equal to the square root of x plus 2. Now notice that here we have this 2 on the outside of the radical, which means if you go back to your idea of transformations here, this should shift our mother function up 2 units. Now in this case, let's go ahead and start a table. I'm going to kind of mix our idea of transformations here with our table values. Now instead of picking our y values here, I know this is a little different than what I just told you to do on example 2. Let's go ahead and just fill in the x values because we know we have to start at 0, right? We can't plug in any negative numbers here for x because we'll be taking the square root of a negative, which is not possible. So if we start at 0, that's a good one to pick. We can also choose 1 because the square root of 1 is 1. But 2 isn't so great to graph. If I try to plug in 2 here, I'll get the square root of 2 plus 2, which is not easy to graph, so I'll skip that one. Which means I'm going to use 4, then 9, then 16, because remember, you can take the square root of those numbers really easily. Okay, so notice that this is just your mother function values here so far. Now for the y outputs, this time when you plug in 0, you get 0 plus 2, so I'll get 0 comma 2. And then if I plug in 1, I should get 3. 1 plus 2 is 3. The square root of 4 is 2. Plus 2 gives me 4. Square root of 9 is 3 plus 2 gives me 5. And the square root of 16 is 4 plus 2 gives me 6. So if you look at this table in comparison to our very first function that we graphed, that mother function in example 1, the square root of x, remember our table looked like this: 0, 1, 4, 9, 16, and then it had the value 0, 1, 2, 3, 4, right? Well, if I just apply that whole transformation idea here and I add 2 to the y values, I get 2, 3, 4, 5, and 6. And if you look here, this is the exact table that you just came up with right here. So it's pretty cool how the transformations, apply to this function here as well. So now you have two different methods for being able to plot that square root function. You can either rely on transformations or you can come up with your own table of values. It's really what you decide, whatever you think you're quicker at, it's up to you. So I'm going to go ahead and plot. We have 0, 2, then 1, 3, 4, 4, 9, 5, and 16, 6 is off the graph, so somewhere like right here. Okay, so there's my square root function. Now if we talk about the domain and range here, for the domain, the x values here, if you look at the cutoff, none of this part of the graph is graphed, so that means x is 0, right? If we go to the left-hand side here, all of the x values are greater than or equal to 0. And for the range here, our low point here is at y is equal to 2, but all the values continue to go up towards positive infinity. Okay, so we have y is greater than or equal to 2. All right, on the back side of our notes, we're now going to be graphing equations that are called relations. So again, tomorrow we'll talk more about the differences between functions and relations, but for right now, let's just take a look at example 4, okay, and just kind of get a basic understanding of what a relation is. Now typically when you see a function that you're supposed to graph, you'll see y alone isolated and then something happening usually to x. So like for example, it could be the absolute value of x plus 3, or y is equal to x squared plus 3, or y is equal to x plus 2. But in all cases, usually the y is isolated, right? And then you're asked to graph, which these are all referred to as functions. Now in this example though, notice that the x is isolated and something's happening to the y. Okay, the same thing down here in example 5, right down here, you see x isolated and y is being squared. So that's kind of a general understanding of what a relation is. Now when you graph this particular relation, x is equal to the absolute value of y, once again we're going to choose y values. So I'm going to start with that -2, -1, 0, 1, 2 list that we typically start with. And in this case I definitely can plug in -2 in for this y, because you can take the absolute value of -2. So it's not like a square root function. Don't think you can't plug in negatives. Here you definitely can. So if I plugged in -2 here, I get an x output of 2. The absolute value of -2 is 2. So if I go ahead and fill in the rest here, the absolute value of -1 is 1, absolute value of 0 is 0, absolute value of 1 is 1, and absolute value of 2 is 2. So if I go ahead and plot these now, I have 2, -2, 1, -1, 0, 0, 1, 1, and 2, 2. Now remember, I'm not plotting every single point on this particular relation, but I could, if I wanted to, I could continue to fill in table values here, right? If I tried -3, I'd get an x output of 3. So I know that this is going to continue in this pattern like this. Okay, so it's definitely very similar to our functions that we studied, y is equal to the absolute value of x, except for this time it's opening to the right. So our origin here is still the vertex of this particular V shape here, but it just opens to the right as opposed to y equals the absolute value of x. This opens up, right? That would be our, absolute value graph there. All right, so let's now talk about the domain and the range of this relation. Now for the domain, we're looking at the x values, and you can do this two different ways. You can obviously look at your graph, but you can also take a look at your table of values here. Notice that all of these values here, none of them are ever negative. When you take the absolute value of y, the output here is always going to be positive or 0. So that means that the domain is x is greater than or equal to 0. You can see it clearly from the graph as well. None of these values, these x values here, are plotted whatsoever, right? These negative values. So your range, or your domain is x is greater than or equal to 0. Now for the range, this time, there is no low point and no high point on your graph, right? This continues to negative infinity and this continues to positive infinity. So here for the range of this particular relation, it would be all reals. All right, so let me clean this up a little bit, and then we can move on now to the next graph here. Okay, so in the second graph here, we're going to still graph this relation x is equal to the absolute value of y, but this time our domain is restricted to just positive reals. So let's think about what positive reals means. That means x is greater than 0. Now, if you go back to the domain in your original graph here, this is really close to that restricted domain. It's just including 0 here. So what this is saying is your graph is going to look almost identical, except x cannot equal 0 in our new graph. So the only coordinate here that is not going to be graphed in this new graph here would be our vertex, which is where x is equal to 0. So I'm going to have an open circle on x equals 0 because it's not included in a positive real domain, and the rest of the graph looks the same. These are all positive x values, right? Positive 1, positive 2, positive 3, positive 4, positive 5, and so on. Okay, and there it is. So I know some students get really confused with this whole idea of positive. They look at this portion of the graph and think, well, those are negative values, but that's negative for the y, right? It's not a negative x value. All of the x values here, you have to look left to right. These here are what you're looking at. Don't look at the values, here. So these are all positive x values. So I know I have graphed this correctly within this restricted domain of positive reals. Now, when we talk about the range, once again, this is going to continue to positive infinity, right? This continues towards positive infinity. These y values continue to get larger, and these y values continue to get smaller and smaller because they get more negative. So this goes towards negative infinity. The only value that's not included in this, so it's all reals except when y is equal to 0. That's not part of the graph here. So we're going to write all real numbers except y cannot equal 0. And there you have it. That's the rest of that graph here. Okay, in example 5, once again, I'm asked to graph a relation x equals y squared minus 1. So I'll go ahead and make my table and select y values. And I can use that standard -2 to 2, because you're not trying to take the square root of a negative or anything, so that's okay to plug in negative values for y. Now when I take -2 and I plug that in, I get -2 squared, so that's positive 4 minus 1 to give me 3. So I'll go ahead and plot the point 3, -2. If I plug in -1 here for the y, I get 1 minus 1, which is 0. So I'll plot 0, -1. If I plug in 0 for y, that gives me 0 minus 1, or -1. So -1, 0, plotted is right here. If I go ahead and plug in 1, I get 1 minus 0, which is, or I'm sorry, 1 minus 1, which is 0. So I'll plot 0, 1 right here. If I plug in positive 2, I get 4 minus 1, and I get 3. So I have 3, 2. Okay, which is right here. Now, if I were to continue plugging in y outputs or y values here, like -3 or positive 3, I hope you realize that you will get the same x value, okay? Because if you square -3 or positive 3, you get the same output, right? 9 minus 1 gives me 8, and 8 here. So I have 8, -3, and, oops, that's not -3, and 8, positive 3. And as you can see, this is that relation here. It's our parabola just opening to the right. So for this particular quadratic, when y is being squared, this time it's going to open to the right or to the left as opposed to up or down when we have y equals x squared, okay? So it's kind of interesting. It's similar to what we just saw with the absolute value of y, how that opened to the right, okay? So the absolute value of y opens either left or right, where this quadratic here, this parabola, will open either right or left. Now if we talk about the domain here for the x values, so we cut off here, right, that's the left portion of our graph here, x values are greater than or equal to -1. So our domain here is x is greater than or equal to -1. For our range, if we look at, bottom to top here, there is no bottom because this continues to negative infinity, this continues to positive infinity. So we have a range here of all reals. Now, for the second graph here, we want to graph our relation here within the restricted domain of non-positive reals. So let's think about what that's asking for. What this means is we want to graph negative x values as well as 0. So negative x values and 0. Well, most of our graph is actually in the positive x values. If you look here, these portions of your graph have x values that are positive, right? These are all positive x values. So we don't want any of this graph here on the right-hand side of the y-axis. We only want this tiny little portion of our graph right there. These all have negative x values or 0. So I'm just going to plot those few points and then connect them like that. So that's our graph here for a domain of just non-positive reals. Now if we talk about the range here, we have a low point, we have a high point, right? The graph does stop. So our range here goes from -1 to +1. Okay, there's our range. All right, in our very last example here, number 6, we have a relation x equals the quantity y minus 1 squared. So let's go ahead and set up our xy table. We'll plug in y values. And this time, just make sure that you're doing order of operations correctly, because when you plug in -2, you want to subtract 1 first and then square the whole thing. So that's -3, then square that, you get +9. Okay, if we plug in -1 in here, we get -1 minus 1, so -2 squared is +4. If I plug in 0, -1 squared gives me +1. If I plug in 1, I get 0 squared, which is 0. Plug in 2, I get 1 squared, which is 1. Now, you can hopefully pick up a little bit of a pattern here. If you look at these values, this is kind of like your, this is going to be your vertex here of this parabola. But my next point, let's say I plugged in 3 here, I'm guessing that I would get 4 as my x output. So if I plug in 3 here, take 3 minus 1, you get 2, and you square it, you do get 4. So you can kind of see that the values sort of mirror one another. As they hit that vertex, they're going to start repeating. So the next coordinate I could also plot would be 9, 4. So if we go ahead and graph those points, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3, and 9, 4. Once again, you can see I have a parabola that is opening to the right. Okay. If I talk about the domain here, my x values are always greater than or equal to 0. Okay, none of this over here, none of these x values are being used. So none of the negatives are being used. X is greater than or equal to 0. For the range, this goes to +infinity and -infinity, so this is all reals. All right, in our last example here, we want to graph this relation within the restricted domain of just non-positive reals. So if we talk about what that means, that again is listing negatives as well as 0. Now, if you go back to your original graph, most of your graph lies within positive x values, right? This whole portion of the graph is positive x values and positive x values. So the only point that we're going to plot whatsoever is right on 0. The coordinate 0, 1 is going to have a closed circle, and that's all that we can include because we don't want any positive x values. So none of these coordinates here would work. The only one that's going to work is this point 0, 1. All right, so it's a pretty interesting graph. It's really boring, but the range here is just y is equal to 1. It's just the one value, and you can even put it in set notation like that. You can either write y is equal to 1 or just write it in set notation. But that is the end of the lesson, guys. Make sure tomorrow you come asking good questions and be ready to work. Nice job. See you in class tomorrow.